orthogonal matrices are matrices given by these orthonormal bases. So last time we finished off with ONB. So this is O for orthogonal, N for normalized, B for basis. Okay, it's orthonormal basis. Orthogonal means that every element in this list would be perpendicular to each other. Normal means their sizes are 1, right? And basis means that you have enough to represent anything in the vector space. Okay? So we talked about the Gram-Schmidt procedure to get an ONB from any given basis, right? If you have any given basis with a given inner product, you can always follow this Gram-Schmidt process to get an ONB. Right? Now, if you take those basis elements and let's say your V1 is the first vector in your basis, then you have V2, and so on, then you can make an n by n matrix, right? So we're assuming that so this time it's a bit more complicated. We're assuming that there is already some standard basis that you represent this first vector in the basis as a column matrix, right? We can do that, right? If you have any vector you can represent using a basis. So we're going to assume that there's a standard basis, but then there's another set of basis. So let's call that standard basis as A, and then this basis is B. And V1 will be the very first element in the list B. And V1 as a column vector is really V1 represented as with respect to this standard basis A. So let's say something like that happened. Okay? Then we have this n by n matrix because we know that the original vector space is dimension n. This will be n by n matrix. And if I call this matrix as capital A and compute A times A transpose, A transpose times A, if I do that, then something interesting happens because what's transpose? It takes all the columns as rows, right? So you end up with V1 as a row, V2 as a row, Vn as a row, multiplied by V1 as a column, V2 as a column, Vn as a column. And then just do the matrix multiplication, but matrix multiplication is same as the regular dot product, right? We know that. That's how we do multiplication of two matrices, right? So when I do this times this, we're really doing V1 dotted with V1, okay? Or V1 inner product with V1. Now, question. What is V1 inner product with V1 same as? Anything with this, any vector with this self, inner product that is same as? Magnitude squared, right? Yeah. But then, because V1 is from an orthonormal basis, right? What's the size of V1? 1, because it's normalized. We made everything unit vectors. So this must be 1. So what we see is that the far top left corner should be 1. Do you agree? Okay, now let's look at what's the next one. It should be this times this. So now we have V1 dotted with V2. What's that? Given that it's an ONB, orthonormal base, orthogonal, right? What does that mean?
Would it also be 1?
No.
I think it's 0.
0. Why?
Because they're magnetic to each other.
They're perpendicular. Yeah, they're perpendicular. Yeah. Two perpendicular vectors, they have the dot product 0, right? Yeah. So it would be 0. And then that will be true for anything else. Other than V1 itself, this times the next one, this times the next one until the last one, it will be all 0. Right? And then you go to the next line, you do V2 with V1. V2 dotted with V1, what's that? 0. What's V2 dotted with V2? 1. Okay. What are you getting at here? It will be a diagonal of 1s. What is this matrix?
Identity.
This is the identity matrix. Okay. Oh, then this tells us something else. See, if you have something times itself and you get the identity, we call this what? The inverse, right? It's the inverse matrix of A, right? So what we just showed is that this calculation immediately shows that A transpose is equal to A inverse. And not only that, A dotted with A transpose will also be the identity, because if this is true, then this should also be true, right? And that gives you another non-trivial fact that if you take orthonormal basis and write like that, and if you read off the rows will again be orthonormal basis. It's very strange, but it is. Okay? So if you have columns of orthonormal basis and you build a matrix, and if you read off the rows, it will again be orthonormal. Okay? Furthermore, and this I don't know how to prove, I can't think of how to prove this statement, but if you have any matrix, I guess it's kind of obvious, right? So A transpose equals to A inverse. If this is true, then we know that the columns of matrix A will be forming an orthonormal basis. Also, the rows will form an orthonormal basis. Okay? So this is really it's vice versa. If you build a matrix with orthonormal basis as their columns, you end up with a property like this. Their transpose is the same as the inverse. And if you have any matrix that satisfies this, then you can see that their columns form on orthonormal basis. Right? So that's why this has a name. Anything that satisfies this identity is called orthogonal matrix. So let me write down a definition. If an n by n matrix A satisfies A transpose times A equals to identity, we call A an orthonormal matrix, orthogonal matrix, orthogonal matrix, orthogonal matrix. And the set of orthogonal matrices are usually denoted by O. So ON is the set of orthogonal matrices in dimension n.